Hey, how's it going? This is Charles from Markforged. I am joined here by special guest, Rob Ortiz from Keyence, and this is probably a bigger production of a webinar than you were expecting. Usually you see me with my slideshow and I'm just talking at you for like an hour. Today is a little different. I don't have slides, for better or for worse, and what we're going to talk about today is the process of reverse engineering a part using 3D scanners and 3D printers. Rob here is subject matter expert in 3D scanning. He's at Keyence, and we have here on that side their VL scanner. So, Rob, why don't you introduce yourself, and we'll talk a little bit about what we're going to go through today.
Yeah, sure. So we're obviously talking about 3D scanning capabilities and kind of the connection that it has with reverse engineering of parts, and then how that can interface directly with 3D printing to be able to take care of some of the scarcity issues that companies are dealing with right now. So we're all dealing with backlogs in components and things being on a shortage, or just the lead times of components can be really hard. And that's just one half of the equation, right? The other half of the equation is there's lots of parts that we'd want to be able to redesign, rework, but we just don't have a model for it. Either it's an OEM part, or it's a legacy component or whatever. So there's a lot of need right now to be able to take data and just do more with it, to be able to understand a lot more of what you can do. And that's where scanners come in. So traditionally, companies have taken their calipers, taken their micrometers, taken their tape measure, spent hours, days, being able to capture all that data. Scanners have gotten to the point where I kind of joke with people that when you connect a 3D scanner with a 3D printer, we're as close to a Star Trek replicator as you really can get. And it's a lot closer than I think a lot of people even believe.
Yeah, and it's still not the Holy Grail, right?
No, absolutely not, right?
We're
There's
not
a lot
there
way
yet.
to go, but it is one of those things where it's definitely capable. And I mean, when we started some of this conversation, I'd sent you over some STL files. We said, hey, here's some parts that we were able to scan. What can you do with it? And you were able to produce some of these really, really nice prints in fairly record time. And that's what I think people would be really interested in, kind of hearing a little bit about what that journey looked like, what's needed, what's the process, that sort of thing.
Cool. Yeah, and so while you're here and still paying attention to me, or to us, I think there are a few takeaways that I want you to come away with here. It's not the Holy Grail, like we're saying, but it is really close. What it comes down to is the tools that you choose to use, and making sure that you are measuring what matters and building what matters, right? There are a lot of features in parts. You look at a cast component that are designed for manufacturing related features that are like pockets, certain wall sections, like thicknesses. Like those are things that you don't necessarily need to reproduce all the time for 3D printing. 3D printing gives you some more flexibility, but it also comes with its own set of constraints. So that's like one of your main takeaways, is like just like focus on the important features and build from there. In good vision, it's like good vision is really important, but that doesn't necessarily imply that you have good inference capabilities. So software can give you good vision, but it might not be able to tell you exactly what you have there, right? Like we can tell when we look at parts, that's like very clearly a hole. Sometimes if it's obscured, you're not really sure. That's a radius, I'm not really sure, but it's getting a lot smarter. So we're really getting close there. So what I want to talk about now, I'm going to hand it over to Rob, and we're going to talk about so Rob, walk us through what it's like to get a scan, to process a scan. Like from the point of you getting a part in hand to getting me an STL, like what does that look like?
Yeah, and so that's going to depend a lot on the scanner. So you can find scanners right now that range anywhere from a couple $100 all the way up to hundreds of thousands of dollars. It's not all that different than printer technologies as well. The main difference is going to be the speed that it's able to scan, the accuracy of its scan, and then just how easy it is to use, right? If you're more of a tinkerer, there's scanners out there that are great. They'll give you a selection of, you get a half dozen STL files, and then you can stitch those together, merge them in different ways, and get a final model. From an industrial standpoint, sometimes you just want to be able to put the part down, push a button, walk away, come back, and you have a fully finished model. So the process that I go through, first and foremost, especially using the Keyence scanners, is I take a part, and I just try to understand, okay, what is it that I really want to know about this part, or what is it that I want to be able to replicate? Right? There's certain features on here that might be critical to what you're trying to use. Now, some scanners are fixed position scanners. So like the Keyence scanner is a fixed position scanner. It means that the camera is at one place and then the part is what's actually rotating and moving. So I'll place the part kind of right in front of my face at about a 45-degree angle, look down at it, and that gives me an idea what the scanner can see. From there, all I'm going to do is I just press the scan button, and I'm going to get a full scan file of what that part looks like. So here is a scan ready to go of that part. And this scan takes about 6 minutes. So we're not going to do it here on the webinar because it'd be boring to just watch for 6 minutes. But there you have a fully finished scan, and it's in full color. So you're grabbing the actual color data of this as well as the actual dimensional data. To then stitch a backside onto it, all I need to do is say, hey, I want to go and grab the other half of this part. So I'm going to say, hey, I'm going to grab this part, I'm going to flip it over, put it back onto the stage, grab the other half of it. And then in order to stitch the two halves of that together, what I have over here, let me open this up a little bit, make it easier for everybody to see. So here will be the top scan. If I flip it over, you can see I'm missing all that back data. And then here is the bottom scan, and I'm missing that top data. Now, all I have to do to merge these together is double-click on anything that shows up in both images. And that's it. Now I have a fully finished, ready to go. I hit precise alignment to let it do its final stitching, but I now have that STL file. And the system will do a lot of the cleanup for you.
Oh, so what we have there is actually already a mesh?
That's already a mesh.
Huh.
That's it.
Huh.
It's all set, ready to go.
I remember working with scanners like a few years ago, and it was like, you get this point cloud, and first you gotta like go select a bunch, like you have to clean up all the stray points. It's like the scanner is just kind of like, you're spraying whatever you have, or with your line laser, and kind of like, in a way, like spraying laser dots, and you're just saying like, okay, like I'm gonna take this, and then I have to clean it all up. So in some sense, I have to be like pretty precise with it, and then, so this, I don't have to do that.
No, and that was kind of the core concept for the Keyence scanner was speed, accuracy, ease of use. So the scanner is going to be able to grab hundreds of millions of data points. You're looking at between 6 to 10 minutes total time. That's including any cleanup that has to happen. To the point where you get a finished STL file that you can drop into Eiger. And then just ease of use. So it's 2 buttons that you press. It's a scan button, and then you're going to double click on something that shows up in both places. And then, as you kind of mentioned, where some of the evolution in scanning has gone is when it comes to the point clouds, right? So you had mentioned you kind of grab your wand, your laser, and you're scanning all over, and you're just shotgunning data points all over the place. The big problem that scanners have right now is we've reached a point where we're able to capture more data than we can actually process. So it's a bigger problem of like signal to noise ratio than anything else. We grab so much data that it can take 30 minutes, an hour more to stitch and scan all of that together. One of the things that Keyence focused on is our system smart enough to recognize geometry. So when you take a look at an actual STL file, so right here is the STL file that we just did, what I can do is if I take a look at the actual point cloud to it, it's not just an even spray of data points. It's actually increasing resolution at edges versus when it's doing just a flat. So it means that I'm able to get the actual surface. So if it's a hole, for example, it's going to say, oh, hey, that's a hole. I need to keep all the data there, versus a plane where it says, hey, that's a kind of a flat plane. I don't really need to grab as much data there. So we're lowering the amount of stuff that it has to be stitching together and processing, and that's what lets it run so quickly.
Okay, so it's still gathering all the data.
Yes.
It's still gathering all the data, but it's sort of selectively saying we don't need those, so I'm not going to burden the computer.
The processor.
Yeah, the processor. Like, if it has to represent on screen every single point, like every time you rotate, it's like, okay, like I'm just going to be dragging and dragging and dragging. So yeah, that definitely makes sense. That it's the software is where the advancements are really.
I mean, yes, we all have seen that, and we've experienced that on the 3D printers and on all the other pieces of equipment. The software is really one of the big determining factors for it. Now, once you finish the scan, once you've got that STL, it's all nice and cleaned up, the data points have been reduced to just keeping the most important ones, that file comes out as an as-is part, or sometimes referred to as an as-manufactured part. And so that's important when you start the next step of your development process, because what it means is when I take a part like this, there's a flat plane here. Now, we probably know that this was intended to be a perfectly flat plane, but in reality, you can't create a humanly perfectly flat plane. I mean, we're talking about scanning things down to the micron level of accuracies. So there's going to be some surface imperfections on there. So when that comes across, it's going to come across with those surface imperfections. And you have a decision you have to make. Are you more interested in the part as it was made, or are you more interested in the part as it was intended to be manufactured?
Yeah.
And that's kind of where the next decision comes in.
Yeah. And that's like an applications thing, right? So if you, depending on what you're making, or what you're scanning, if it's like, imagine that I'm a foundry, right? So I have been making cast iron components, let's say in the plumbing industry, for the last 100 years. And I've got these molds, right? I've got patterns. And the patterns are 50 years old, kind of wearing out. You take that, but it's like, it still works, but you have, maybe you've used plywood as the backing plate, and that's kind of rotting, and you need to remake it. Well, 3D printing is actually really good for making patterns, but if you were to go redesign something that's been handworked, it's going to be really hard, right? You've got these gaps, like a master pattern maker is filling in certain areas, removing material, and that pattern was made to be exactly as it was, right? And that way you can get the cast part out that you need. So that's a situation where you're saying like, okay, I need to get it exactly like this. But in a lot of other situations, like if you're looking at machine parts, I don't want like somebody's chatter, right? Like if you like cut this part too fast and like, let's imagine that I've got a machine part and my supplier goes away, but he's made the part with like a bunch of chatter marks on it. Like there are certain surface imperfections, but like I know what it needs to be like, but I don't have the file anymore. Well, we don't want to keep that. We want to reverse this back to its like kind of parametric form. So one of the decisions that I think is like probably general consensus across at least the community that I've engaged with in the additive manufacturing space, if you don't need to scan it, like you look at a part and you're like, that's pretty simple. Like this part here, I probably
right. You get a couple of holes, a couple of radii, and some diameters.
Yeah, like I don't need to scan this, but there are parts that you do need to scan. So that's like probably the first decision. Like in the decision tree, it's like decide if you need to scan it first. And I would say that like based on the number of features, like if you're looking at a dozen features,
I mean, it's a time thing, right? As I mentioned, we can scan a part in about 10 minutes. Can you design it in 10 minutes? If you can do that, then obviously go the route of designing it versus scanning it.
Right.
But then as the number of features continues to increase, then it does become significantly more valuable to try to scan the part. And the other thing to consider is the accuracy too, right? You can model something like that pretty quickly, but you still have to measure and dimension everything to make sure that you get as accurate as possible, whereas scanners can get down into the micron level of accuracy. So those are some of the decisions that also have to get made.
Yeah, and I would say that the way that I've gotten, like in my limited use, working with the files that I've gotten from Rob, the scan works as a reference. That's what it's for, right? And like when you're trying to get back to parametric CAD, it's a great reference, but you want to get out of the mesh as soon as possible. In some cases, like when you want it as made, that's when you can start like working with meshes. And I did not learn how to work with meshes. I don't know that any like engineer learns to work in CAD with meshes, right? We learn parametric CAD, and that's what it is. But like there are certain cases where if you're used to doing surface modeling, if you're an industrial designer, like that's the sort of thing where playing with a mesh, playing with a surface, like that is more suited to you. So there's different use cases here.
And it depends. I have a little bit more experience on the 3D printer side of it. I've never had any formal CAD training. And so for me, I'm a little more comfortable actually using meshes.
Oh, good point.
So it all depends on where you kind of started from.
Yeah.
So like just as an example, right? So a part like this, which we took and we kind of used as an example for a replacement component. So in this case, it's a seal of some sort of bushing or some sort, I'm assuming. But if this is a part that needs to get replaced, well, I may not know everything that was intended as far as this part is. I just need it to be able to fit into the machinery and create the spacer that needs to happen, or maybe it's a gasket, right? If it was made of a gasket type material. So in those instances, we can go straight from mesh right to printing because I don't know what it was supposed to be, and there's some slop in the tolerances.
Yeah.
Plastic parts, for example, sometimes you can also go straight from mesh right over to the printer.
Right.
When you get into some machined parts, that's obviously where you definitely need to be able to smooth things out, make sure a plane is a plane, make sure a cylinder is a cylinder. So we'd scanned this part, and then we were able to actually send it over to get printed. And what do you think was the time frame from when I sent you the STL file of this to when you were able to get it onto the printer to start the production process?
Yeah, so we can actually, we can talk through, let me see if I have the, one is the one that I wanted to point out. You know, I don't have the,
they're all pretty similar.
They're all pretty similar, but that might be the one. Okay, yeah, this is the one. So, so there are some nuances, like to, as scanned data, and so like an as scanned part that you take and print, and the recaded model. So I'm gonna take you into Eiger and into my little CAD package and just show you what I'm seeing and what nuances there are. So let's see. Anonymous attendee got 2 great questions. All right,
okay.
So how can you modify scanned parts? That is, I'm gonna show you that. And then if you scan a warped part, can you flatten it in your software? That's also precisely the issue that I ran into. There was some slight warp in this part, and how that comes out in the CAD interpretation is a pretty critical thing. So let's see. I'm just going to share.
Yeah, while you're kind of getting that up, let me. Yeah. I can explain real briefly some of the options when it comes to editing the parts. So once you have the part, you can bring it into a software of your choice. So let's say you're working with something like a Fusion 360. So there are some capabilities inside of a Fusion 360 to take a mesh file and make it into a surfaced file. Once it's surfaced, you can make some alterations to it. You can add some additional holes and things like that to that. Or if you want to make it into a full solid, you'll begin doing a trace operation. You can do the same thing in some of your higher end packages like your AutoCADs and SolidWorks softwares, where you can use it as a master that you can then extrude an actual solid off of that object from. And because it's dimensionally accurate, you're really just saying, hey, I want to extrude to this surface, and then I want to extrude to this surface, and I want to set a circle that is of this size, and you're just clicking on the actual scan data that's been imported into SolidWorks. From there, you can make it into a full solid. And if you're working inside a mesh environment, sometimes people use things like a mesh mixer or something like that. They'll do a plane cut just to make sure they get rid of some of that noise that might exist on the edge of a part so that it sits completely flat. Again, that all depends on what your intent is. If you want to get it as is or as intended, so you've got to think about that before you start your operation.
Cool. So I've got Eiger up on my screen here, and what we're looking at is, I'll go into the internal view. I think this is the best way to see it. When you walk through the layers, we're actually going to see that we're going to see the warp. So this is the very bottom of the part, and the scan sort of picked up like a bit of a curve, or maybe one of the corners is kind of bent up.
Yeah, I think the part actually is bent.
Yeah,
I think it's not completely, because it kind of rocks a little bit.
Yeah, so I see that all the time when you're reverse engineering a broken part. This is like, I've done this before. This is something that I did actually just like about 4 weeks ago. I had a door lock component just break. It was a cast part, and after many years, probably over 50 years in this house, and like people kind of jerking on the door frame, it's like it broke, and my door wouldn't open, so I had to like jimmy the thing open, and I took the lock component out, and I've got this little piece. I had to super glue it together. Right, but like, do you trust my super gluing technique? And
I don't know. You might be a pretty accurate super gluer.
Yeah. So what I ended up doing is remaking it. Right. I didn't say, like, I was going to scan it. It was like, well, I don't really trust this, and it's kind of worn out. So, but that said, it's a great place to start. So first, I'll show you this this flatness issue that I have on screen here, and this is kind of what's showing in Eiger. Hopefully, you can see it, and you've got yeah, it's like mostly there, but there was that base that was just wasn't flat. It was warped. So when you have a warped part, it's going to pick, and you orient it on the build plate. It's going to pick the lowest point and put it on. So I mean, I can only zoom in so far here, but like this is the surface that was down, and then the rest of it actually had to be supported by like one layer of supports, right? It's not very much, but it's enough to make a difference. So what Rob was talking about with the reverse engineering process, I'm going to switch over to my CAD to Fusion 360. I kind of waffle between Fusion and Onshape. Like we don't use we use SolidWorks at Markforged, but we in the marketing team, like,
That's the ever-present issue. Is there's always a plethora of options.
right. But I think the tools are about the same. Like it's not like I'm using the free version here. We are using the paid version, so there are mesh tools, and really the concepts are the same. When I do the walkthroughs for SolidWorks and I do the walkthroughs for Autodesk, it's about the same. It's you take the mesh, right, and maybe I'll just press the play button and see what it does. So, oh, is it going to do it? Yeah, so it's going to kind of walk through, and what I've done, no, it doesn't want to do that. So I'll walk I'll walk you through step by step here. So I've got this mesh body that I imported, and you can kind of see some of the warp that's going on, right? There's like kind of like a bulge here. There's a bulge here, and that's just a result of the manufacturing process, right? But if you wanted to get it as is, like what I end up doing is kind of taking the mesh in, and then oh, it really doesn't want to do that. I'm importing the file, and then first setting up like where I think the center point is, and then what it's able to do is take you can take a section cut, right? And that's where we're saying like, let me build a plane, and say like, I want the intersection of this plane with mesh, and it's going to give you like a set of points, and it's going to make you a sketch here. And that sketch, if you look at it, is like you can use these tools here to create fit curves to mesh sections, right? So if I'm going to do a fit curve, what I've done is I've used the circle and kind of done fits to the ODs, right? The ID and the OD of this ring at that cross section, and from there, I'm rebuilding it. So that allows me to at least know where the center is, so that I can start rebuilding. I then built another section cut, and this is going to say. I then sectioned it along the XZ plane, and I've switched over to creating a section this way, and oh, it really doesn't want to show this. So I've created this section here, and so it's taking that section cut and giving you what essentially is rotated around, right? So if you're going to do a revolve that way, I'm assuming that you want pretty uniform thickness on this, so I built, let's see, I built a spline on top of it, and then did offset surfaces for that. I really should pre-record these CAD things. But I'll show you the solid that I made, right? So it's so I've built a solid and just essentially rebuilt the part. And when you look at it this way, it's like, is it exactly the thing that we had before? Not exactly.
Well, and I think if you can actually pull up the scan mesh and overlay it, so you can kind of see some of the deviations in there. So it's going to be,
it's pretty close.
Right. I mean, it's a lot of as intended versus as is. So you can see there's some obviously manufacturing defects or even wear and tear over time between that and then the live scan. and your what you modeled there.
Yeah.
And
yeah.
again, that's the decision you've got to make when it comes to the part. Yeah, you can see some of the red area that's kind of sticking out from your from your model.
So that's essentially like kind of in a nutshell what I've done here. The last thing was like this feels like maybe like an encoder ring of sorts. So it's got 100 of these slots in there, and it's probably so that whatever scanner is able to read each of these, and so as you're rotating, it's saying, okay, we've progressed one space. So that's kind of where we're at. And this process, like even though I've made it look really complicated, it was not that complicated, right? So it's essentially
how much time did it take you when you weren't sitting in front of the webinar trying to do everything live? How much time did it take you to get it ready to go to the printer?
Now that I know what I'm doing, if I were to redo this process, it would take 5 minutes to do that, right? And then maybe 10 if I'm like trying to like fiddle with the mesh. But then like as soon as you get that part into the printer,
then it's hands off.
It's hands off, right?
So it's about 10 minutes on the scanner side. Maybe we'll say 10 minutes conservatively on the you're using Fusion. So cleanup side. So 20 minutes to the printer, and then obviously it depends significantly on the type of part. But a part like this is only a couple of hours to get fully printed up, and now you've got a replacement part. And one of the areas that we're finding a lot of this being used, especially on parts that would be similar to something like this, is in gaskets and seals. So those are parts that, just due to some of the natures of the supply chain that we're dealing with right now, can be in significant shortage. And due to the fact that a lot of those have fancy shapes and fancy designs to them and stuff like that, they've got to be very specific in the mold that they're made to. And so one of the areas that individuals have had a lot of success from a scanning standpoint is you scan. Well, you could scan a broken seal. That's a little bit harder. As we just showed, you got to do a little bit of design to make it back as intended. But if you happen to have a single spare, you scan it, you add it to your library, that is now ready to get printed. And you can print it out in like a TPU or some sort of a flexible material. And due to the fact that in most cases, there you go, there's a TPU seal right there. And in most cases, because they have some flexibility to them, as long as you're scanning it as is, you don't need to do the cleanup process because it'll form to whatever it is it's trying to seal, and you're ready to go. So in those cases, you can go straight from scan to printer. Maybe you'd spend another minute or something like that getting it cleaned up a little.
Yeah. So once I've got this part, once I've got it in, this is the as intended design, right? Mm-hmm. So I've sort of taken the mesh file and turned it into a parametric CAD file. So if you wanted to, addressing the modification question, now that I've got the CAD, if my encoder ring needs to be 200 steps, 200 separate steps in it, or 150, like I can change that, right? So this is where there's some value in being able to get that parametric file. I think a lot of folks, one of the YouTube videos that I watched, which we can probably send out like a summary link of like all the stuff that we think are good references, and
there's plenty of great material out there.
Yeah, and like I would say that I'm no expert. Again, I'm no expert in scanning. I'm definitely no expert in CAD, but like I think I know enough to know what's good and what's not. This guy kind of brings in the file and he says, there's just a lot of data. So to your point, Keyence being able to reduce the data.
That's a huge benefit.
It's a huge benefit.
The fact that you're dealing with a file that can be 4 megs large instead of one that is 4 gigs large.
Yeah. So being able to take that in and work with a file that your CAD program isn't going to choke on is going to be pretty important. But in terms of modifying the part, there's this video is like he's modifying a BMW motor mount to accommodate a turbo, right? So the motor mount before was like 4 bolt points, and then it's got kind of a specific angle, and I think that's where the scanner is really important.
Yeah, you get that dimensionally accurate information.
Yeah, and you know exactly where it's working off of. You're not like measuring and guessing, especially when you don't have everything at right angles. It's going to be really critical to have that scan data. So then you can rebuild off of that. But yeah, the video essentially is saying, like, my takeaways are, you want to get out of the mesh as soon as possible. And you can do that by building these, create mesh section sketches. So build those sketches, kind of build up your solid body. And then when you go to modify it, that's why it's important to have the parametric CAD. So Jack, you had a question here. Are the scanners or scanner able to produce parametric files like STEP or IGES files?
So you can get STEP and IGES files out of a scanner. The thing you have to remember, though, is the scanner sees the world as is. So as I kind of alluded to earlier, on a flat surface, we look at this and we say this is a single plane, and this, in an ideal perfect STEP or IGES world, this would be a perfect plane. But there's some surface roughness to this. And if the scanner is picking it up down to the micron level of accuracies, then it's going to see those surface imperfections. It's going to say, hey, there's a high point here, there's a low point here. And so what we would look at as a plane is going to get turned into a number of triangles and different plane surfaces to include that high point, that low point, things like that. So the answer is yes, you can get those files, but it may not be exactly what you're trying to think of it as being a cleaned up one. You still have to go in and select different points and flatten out a surface if you want to make that a plane. To what I had said earlier, if you want it as is, like on a cast part, you're good to go.
Yeah, yeah. And there's a question here. Spencer, you had a question. What are the solutions for partial scans or incomplete surfaces when going from a mesh to a parametric model? And this is, I think Rob's already touched on this, partially touched on this.
I like that. I saw we went there.
So being able to flip the part and then just like quickly align it, I think that's, yeah.
Yeah, and that's going to depend a little bit on each of the scanners that you're dealing with. So within the Keyence scanner, you can have an infinite number of orientations of the part, and then you just need to select anything that occurs in both images, and it will stitch those together. So on a part like this, I may get all the data on this side, all the data on this side, but there's a through hole on here. So maybe I want to orient the part looking straight up so that I can get that information. I can stitch all those together to create a single file. Now, one of the things is that there's always going to be some features that a scanner can't see. Generally, what we tell people is if your eyes can see it, then a scanner can see it. But there's a lot of features that we're going to want to put a tool down in, or you kind of got to do one of those to be able to sort of see it, and it's just not feasible or economic to get all of the data for that. The other thing is they do have some limits on how deep they can go. So like even on the camera just shows this as being black because the camera can't see deep enough down there. Now I can't even actually see, if I look at it, I just see black in there as well, but I know that that hole connects to this hole. So the scanner won't be able to pick that up because I physically can't even see that. And so when we go to a printed version of that, I don't know if we can. No,
you can see a little bit of the glare if you tilt over. Yeah,
trying to get it to the lighting right.
Yeah, you bring it closer to you. I think it might.
Yeah, get it in focus. Yeah. So you can see that it kind of ends the hole a little bit because that's as far as the scan data goes. And so in those cases, there are ways to clean it up in your CAD softwares. So once we get it converted over, you'll actually have a cylinder here, and then it'll end in a plane, and then you can just take that cylinder and extrude it downward, do a cut that extrudes down to where you want it to go. Or if you don't have that capability and you printed this as is, a lot of places will just do a finishing operation. So we know that's a hole, we'll just drill that one out. There's going to be some tapped holes. Obviously, 3D printers still have some difficulty on getting a threaded tapped hole, so we'll still have to tap some of those to get to the exact final component that we're looking for.
Yeah, and this is, I kind of mentioned this earlier, but vision and inference are two kind of different things. Like as we recognize as a pattern when we look at this part, it's like, yeah, there's a very clear through hole there, but I don't know what's like, maybe there's stuff painted on the surface of the inside there, I don't know, but like I can infer that looking at this that is a through hole, right? But the scanner would have to like, a through hole implies that there's a bore that just goes all the way through. We're gonna infer that it's like a smooth cylinder because it was probably drilled or using, like, since this is a cast part, there would have been
some sort of pin.
Sort of a pin in there that was blocking it. So when I look at it, just like the scanner would look at it, I don't know what the surface exactly looks like, but I can infer, right? So this is where I think with the software over time will get smarter. When it starts to see sort of things like that, where it's like there's like a big gap here, and this is an incomplete mesh. Like that could be a hole, right? Mm-hmm. And then that's where I think there's probably something where it's like Keyence doesn't want to, or like not necessarily even Keyence. It's like any of the software companies don't want to take on the responsibility of having like sort of fabricated or made up geometry that wasn't there. Like they're going to give it to you exactly the way that it is so that you can make those decisions.
Yeah, our goal is to get the data as is, as accurately as absolutely possible, and as quickly and easily as possible.
Yeah.
So like our scanners have the ability of getting down to either 10 micron or 3 micron as far as accuracies go of a part. And that's incredibly accurate, but we do want to get it to you as is so you can make the decision if you want to clean that up or not.
Yeah. And I think, so there's the question of like working with partial meshes. There's another piece of this too. Even if you have an incomplete mesh, if we're going through the process of rebuilding the part in CAD using the mesh section planes, and we're going to go build sketches off of those mesh sections, if you pick the right section, so for example, on these parts, I wouldn't take a section all the way down. I wouldn't take a section like all the way into the part, right? What I want is a section that is visible to the scanner. So if you take a section kind of maybe like a 1/4 inch down from the top of the surface, it'll still see the bore there. So
yeah, very accurately.
Yeah, and so you can then build your sketch off of that and get yourself a pretty nice plane. So you'd have a nice sketch that you could then extrude and do cuts off of. So I think that's probably a pretty key piece of this, is like knowing where to build stuff off of. There are a few questions here. I guess you've sort of already touched on this, but like, what's the model of the scanner, the accuracy? Here's your chance.
Here's my chance. Okay. So the scanner that we've been using, that we did for some of this stuff, and the one that we have here in the studio, it's a Keyence VL. It's virtualizing large parts, and it'll be able to do parts that are all the way out to about 3 foot in diameter and about 2 foot tall. Total scan time is about 6 minutes, regardless of how big that part is going to be. Accuracy is 10 microns for the model that's sitting here. There's another model that does much smaller components. That's going to be 3 micron accuracies. There you go. There's my pitch.
Cool. I mean, that's really fine. And if I'm like, don't hold me to this information. If I'm sort of like back calculating the motion control of our system, like, it's like, if you take like, what does one turn of the encoder, what does one turn of the stepper motor do to the movement of the print head? It's something like 12 microns, right? Like we can really only move. We
specifically designed this guy so that it would be on par with some of the best high resolution printers that are out there. So they're going to be basically the same.
Yeah.
Even if you're looking at other technologies in the printing space, they're all generally around that 10 micron standpoint.
Yeah. How big is the scan volume? I've got a print bed here. The bed size. Don't be confused. It's the printable area is probably something like 13, 10 and a half, and we can build 8 up. The FX20, which is behind me, you can kind of see it in the background over there.
Phased out.
There
it is.
Yeah, that's 20 by 16 by 16. So obviously not. You aren't going to make like cubes 20 by 16 by 16, but like, what's the build volume for that thing?
You can throw a part on there that's 24 by 24 by 12.
Okay, all right, that's pretty close.
With a single push of the button, it'll just rotate and grab everything all in one shot.
Sweet. Okay, so it's like,
I mean, they're designed
size.
very compatibly to go with printing as an additive manufacturing industry. Now, any other questions? Because there's a couple more steps we want to do, at least discuss in the journey.
Yeah, I will. I'll get to questions in like the last 10 minutes. There are a few more, but we can kind of get to those.
I love an active crowd. This is great.
Yeah.
So we talked about, we've scanned the parts. We've talked about, do we want to use it as is or make it do an as intended? We talked a little bit about some of the things that we would do in softwares to then make it more as an as intended if we needed to. We've then discussed, hey, there's going to be maybe some data that you don't get, and how do you deal with that partial data? And you can either make it into the solid and do it in CAD software, or you can do some post-processing if you had printed the part in an as-is configuration. A couple of the other things that you need to think about is orientation.
Oh, yeah.
Right?
Yeah.
And I think you kind of uncovered some of that as you were going through and doing some of the parts. So do you want to explain with these guys, for example, what you kind of uncovered when it came to orientation that you have to at least think about before you go into the printing operation?
Sure. So when you look at when you're going from one manufacturing technology to the other, there are like differences in the way that it's being built and like what's important for each of those things. I think when we're considering cast parts, machine parts, there's usually some flat surface, right? Like you have to have sort of a zero, like an XYZ, like you have to have a Cartesian coordinate system, and it's got to be flat. And with 3D printing, like with the extrusion style printing, with us like doing composites and us doing metals, we have to build layer by layer like this. And with the fibers, they actually require you to orient the fiber in the XY plane. So you're going to get the best strength in the XY plane. I looked at this component and I saw this section here. This looks like probably supporting something, right? Like there's maybe a shaft that goes in there.
That's it's part for a microscope. So it sits like this, and this is actually where the lenses sit. So it's pretty important, because if the lenses are not sitting straight, you're not going to get good pictures.
Yeah. So here in this section, if I were building this part with our X7, I'd want continuous fiber to go into these arms to just like give them the most stiffness as possible, prevent them from warping. If you were to build this in metal, I'd say you probably could print it like this and kind of build these pillars up this way. But if I'm building it in a composite part, like I kind of want to build it like this. So the different orientations, the first thing that I tried was like, okay, well, it's like kind of a big flat part. Like maybe I'll just have it, I'll print it flat like this, right? So I built it up like this, and it does get the fiber into these sections, but what ends up happening is like you end up having to build supports underneath
all over the place,
and it uses a lot of material for supports. So
now that would still be a structurally fine part.
Oh yeah,
right. There's nothing wrong with that. It's just we're being a little wasteful as far as material goes, and so our costs have increased and our build time.
Right. Yeah. So you can sort of see the surface here. It's maybe a little tough to see, but it's not the best, right? It's a supported surface. We don't do soluble supports because most of the parts we're making are intended to be strong parts. But sometimes like the cosmetics may matter. So in this case, I changed the orientation to print like this. Still gets the fiber into these arms, but just makes for kind of a better overall finish. And you're still going to end up needing to drill and tap holes anyway. But this is printed in composites. I think ultimately that part we would want to make this in 17.4 stainless or something else. Like we would want to make this in metal.
It depends on what the use case is, right? If we're just trying to have something that's a stopgap while we wait 6 weeks for a supplier to get us an actual part,
right?
Maybe a fiber-filled onyx material would be just fine.
Yeah, yeah.
But I think it's helpful for people to kind of see. So we'll put those two right there. So if they can maybe zoom in a little bit, some of the features that are all picked up on that, you get a lot of detail. And you're able to print it with a lot of resolution. You can see all the holes are there. We've got everything exactly where we need to be. And kind of just continuing and wrapping the journey from start to finish. So this part took me, I think it was about 8 minutes total to scan.
Yep.
And that's top, bottom, and the through hole.
Yep.
So it took me about 8 minutes to scan it, and then I sent it to you. And then what was your process like for this guy to get this ready to go into the printer?
So there's like kind of taking the as is and as intended steps here. When the as is one, I just did a couple plane cuts and said I want this to be the side that's down. I think the top should be aligned with that. So I also did a plane cut at the top. So it's sort of like just putting it through a channel and like slicing. Yeah, do a little slice like top and bottom. I kind of cleaned up some of the surfaces, and Fusion is pretty good at mesh repair. I think any CAD package, SolidWorks will do a pretty good job with mesh repair too. So it's just going to patch. And in some of these cases, like you may want, if you're making it out of metal and you're just going to probably drill and tap it anyway, like you don't need to get every hole exactly the way it's supposed to be. Like there could be a gap, there could be some material in there, that's okay. But if you wanted to get it all the way, you'd have to spend a little more time. So the steps that I did for this part specifically, I'd say 10 minutes, right? Again, like,
and so
I just didn't spend that much time
as is, right?
Yeah, that's
okay.
That's the as is.
I think that's actually really valuable for people to see too. Is this is the quality that comes out as is. So there's no cleanup. that happened. I know I'm throwing our camera crew off. They're doing a fantastic job. But there's no cleanup. So about 10 minutes of getting it ready to go into the printer. Do you remember about how long it took to print this one?
Let me take
Roughly?
a quick look. This part, versions, about a day. So it was like kind of overnight print.
Okay.
Yeah.
Okay. So
Yeah.
we scan it, we start it printing, we come back the next day, we've got the part, and at that point, 95% of our work is done, and we're ready to go. We've got a couple of holes we've got to maybe drill all the way through or tap, depending if they're even important and critical to the operation. But this part right here, if I had to get a replacement of this, I mean, that's a cast mold, so we're talking tens of thousands, if not hundreds of thousands of dollars to do, plus manufacturing time for that, which could be 2 to 3 months, plus probably some development time in there. And this is on something that's not even my part, right? This is something I was just trying to get a replacement of because there's a massive lead time for these components. And the cost even just for this replacement part from an OEM is about $2,500.
Oh, wow. Okay, yeah. So, I mean, like when I look at a part like this and I think, okay, well, I can't wait for a casting, right? The lead times for molds are incredibly long. You'd be waiting months to get a part. So I'm gonna say, the first thing I'm gonna say is let me go get this machined, right? And I think realistically, to get a part like this machined, like you could do that.
You could.
Yeah.
You're talking some serious machining time to remove from that block of material. But yeah, absolutely could be machined.
Yeah, I'd say like you end up having 1, 2, maybe like 3 or 4 setups, right? Like, so you could probably do 4 setups, and it's a pain, but like you could do it in machining. But you first have to get to the point of having a file. Like, if you were buying this from a supplier and they wouldn't give you the file.
They're not going to give you that file, right? So even if you're going to a CNC machine, you've got to get the data somehow. So if we drop that off at a machine shop and said, hey, can you make me another one of those?
Right.
Even with somebody who's pretty good with measurement tools and building it in CAD, I mean, you're probably talking 8 to 12 hours just to model that.
Right.
And that's not even accounting for the fact that you've still got to dimension and measure every single one of those holes, those fins, those diameters.
Yeah.
I mean, you're talking 3-4 days of man hours of time before it even hits the CNC machine.
Yeah, and that's what we're all here to save, right? Like, I think we're all kind of in a pinch here, as far as time goes. There's like too much to do, not enough time to go around, not enough people to do it. I think scanning is going to help you. Scanning and printing together will help you get something in hand faster. Like, this is one specific part, right? I don't want to like generalize too much, but always consider what your most cost-effective option is for making things. It might be machining. It might be 3D printing. And when I say 3D printing, it could be binder jet, right? We don't do binder jet, or sorry, we don't do like multi-jet fusion. We're not HP, but like that's a good process for making parts. And I'd say like for some like injection molded components like this, I would probably go with that over our system. But when you're looking at a machine part, cast parts, those are some good candidates for us.
Mm-hmm.
So consider what your manufacturing process is going to be, and then kind of build off of that, right? So we're looking at, so with this specific part, we're saying if you were going to go to machining, you wouldn't have to figure out all those pockets and stuff, right? Like you can just kind of build a really simple model off of it. You can take those planes, do the section cuts, figure out where your holes are. You can do some manual measurement to figure out what the thread pitch is, but like you got to build from somewhere. And I think the mesh is maybe the easiest place to start. Otherwise, yeah, you've got calipers and you're just measuring and making a bunch of different sketches, when in reality, you just needed a few critical surfaces. So that's kind of my take on like the way that you get to a file. Mm-hmm. The mesh is a reference. Yeah, so we've got sort of like we've got about 10 minutes left.
There's a lot of questions that came in, so let's just kind of rapid fire through some of those.
Yeah, cool. So first one's really interesting. This is application based. Tiago is asking about using additive and scanning for paper pulp molding. And this is actually something that I investigated 3 years ago. There are a bunch of case studies out there that you can read. We actually haven't produced one, but there's something really interesting that we can do right now, which is to build a part with no walls, is to take the shells off and use the gyroid infill. So that allows you to have airflow pass through.
Which is still the coolest looking infill I've ever seen.
It's super cool. I wish I had an example here. But gyroid infill essentially is modeled.
Yeah, it looks awesome.
It's like
I would hang that on my wall.
Yeah. It's modeled off of essentially it's kind of like bio-inspired infill, but you're going to be able to have pass through of air that goes out. So with paper pulp, you are kind of taking a slurry, putting it onto the mold, and then you want to draw vacuum to pull it in, and then you want to like expel air to push it off. So there's like a lot of these processes. I do think that some combination of, like, you could take a part that was made from that process, scan it,
get the shell from
get the
that,
shell,
right, and then the infill will come in automatically.
Yeah.
And then you would just print it without walls, and you get the sphere of infill that allows the air through.
Yeah. So that's. Do you have representation in Brazil?
We do.
Okay. Cool.
Yep.
So
you reach out to Keyence.com.
Yeah.
Keyence.com.
Yeah. We'll put you in touch. What's the software for stitching called?
Inside the Keyence, it's just the Keyence Scan software.
Okay.
So that's just part of the system. It's included with it, no additional charge. There are other tools out there that can do stitching for other scanners. One of the ones that I like the most is made by a company called Octon, O-Q-T-O-N. They used to be Geomagic. They have their Control X software and their Design X softwares. Those are really good for stitching together other scanners that don't have the ability to auto slice or auto stitch the 2 halves or 3 halves, however many, together.
Cool. Let's see. This is a good comment. The original encoder ring had normal manufacturing and age deviations from the original nominal design. You recatted from the scan cloud info into a best engineering judgment of what the original reprinted part should be, the new nominal. So do you ever manually check with classical hand instruments perhaps some dimensions of a scanned part to see how they might match or differ from the mesh obtained? There are 2 things here. Yes, we can, and I do always check with calipers, even though, like, calipers, I use calipers. You could probably, with this one in particular, use a micrometer, which will get you closer, like a more reliable measurement. Like calipers, I'm just like sort of fiddling, and like I do it a bunch of times. It's like, okay, like I measured 15 times and like got within this range. Like that's pretty good. CAD package has a nice tool. It can do the deviation. It'll show you the deviation from your part. So SolidWorks has this option, which I've seen. It'll give you kind of like a what is that called? It's like
it gives you a
gradient,
deviation,
right? Give you a deviation gradient, yeah.
Yep, and you can even get it as like a histogram.
Yeah.
One of the things that we find quite often is inside the Keyence scanner, it actually has the ability to, you can scan the original, scan the print, and then overlay the 2 of those and see the deviation. So even though both of them exist in the real world, you can still do a deviation between those.
Yep. Let's see. So question here is about how do we handle the draft of the part, especially in a hole or any rectangular cut. So the draft is something that, like, the scanner will pick up.
Correct.
Right?
Yep.
So if I were to be really diligent about what I was making, so the 3D printer does not care about draft. In fact, like, if you have a pocket, get rid of the pocket. You don't really need pockets in a 3D printed part. Well, sorry, you don't need pockets in an FDM 3D printed part, like in an extrusion part. In binder jet, you will want pockets.
Yeah, we have powder that you need to get out.
You got powder that you need to get out. You don't want to like do that fully solid. It's a waste of material. It ends up making the part really heavy. But for us, I don't care. I'll take that section and use my own infill and fill it in. I'd rather have that than the open pocket. But when we're talking about draft in some of these hole features, that's like to your interpretation. If you were to take 2 planes, do those mesh sections, and then do, say, a loft from one to the other, then you've got your draft sort of figured out. But when I'm building the model, I'm just going to say, let me give it an arbitrary draft angle and maybe make the adjustments so that it matches the mesh, if that's what I'm trying to go for.
Yeah, and I think it depends, because if the intent of needing that draft is because maybe you're making a mold,
Right.
Right, in which case you need the draft
Yeah, you do
because
need
you
the
want to be
draft,
able to
yeah.
pull whatever it is out. The scanner's going to pick up the draft, and then if you're making it as is, the draft is going to be in there. And then even if you're bringing it into a CAD software to do it as intended, you should see that draft, and so you can add that in and make sure that it's part of it. If you forget, then that's where those CAD compare tools will say, hey, there's a lot of deviation here at the bottom edge of something because you made it into a cylinder as opposed to into a cone.
Yeah. Let's see. Questions here. A lot of software questions. So, how much does the software cost?
So yeah, so the software is technically free. It comes with the scanner. I think the better question is how much does the scanner cost?
Yeah.
For that one, what I would suggest is if you reach out to us directly, we can help and figure that out because there's a huge range of options. To give people a general idea, they'll go anywhere from about $40,000 all the way up to $120,000. So it really depends on the stage size that you need, the accuracy that you need, how automated do you want it to be, things like that.
Yeah. And as far as manipulating the mesh file goes, I use Fusion. I think Fusion is like a pretty cost-effective way. If you're in the education space or if you're a hobbyist, it doesn't actually cost you anything. There are features that are paid only, right? So if you're doing like a lot of the mesh modification and interpretation stuff is going to be paid. Relative to some other CAD packages, I would say Fusion is very inexpensive. That's why they allow the marketing guy to use them.
Yeah, Mesh Mixer is a free one that's used quite regularly, and then Fusion, the free version, does give you a lot of capability. I think the paid one's only like $500 or something like that. It's very, very low cost, and that adds a huge allotment of mesh tools in. And legitimately, that's a lot of what you would need. The only other thing you might want is from a software standpoint would be something like a SolidWorks, but you don't need a high-end CAD package to work with scan data to get it to a printer.
Yeah, I think if the value of your application is high enough, it's worth it, right? It's like, in fact, if the value of your application is less than the cost of the software, you might consider finding another way to do the thing. So I do think that over time, like we've already seen this in pretty much any industry, like over time, the cost of the equipment, service software just continues to come down over time. So yeah, in 10 years, like you can walk to your local convenience store where there are no attendees, it's all robots, and like put your part into the bin and like you'll get a replicator part that same day probably.
We're able to do that to a small extent with some, I mean, parts like this, we're 20 minutes of total operation time to get it started.
Yeah. So a lot of software questions. If I don't get to your questions, we will follow up. But here, let's continue to like kind of go through these. And if you want to hang on, you're welcome to. We've still got 230 people on the line.
Happy to answer the questions.
So what are 3D post-processing methods you use to make sure hole locations and diameters are perfect? I don't think
that's pretty similar to what we just talked about on the draft side of things.
Yeah.
So the scanner will get the hole position to whatever its accuracy is, to 10 microns in the case of the one that we were using here. So that's already in the mesh file. If you're printing as is, then that hole is already there. If you're doing it as intended, well then once you're finished building the solid from that, you can do the CAD compare to see, hey, is the hole lining up with where it should be or where it isn't? It might actually be helpful. I can even show what a CAD compare looks like for everybody. So here I have the part that we did, and then I'm going to compare this to another 3D print. This is not the 3D print that we did here. This is being compared to one that was done on just a very, very simple Ender 3. So please don't hold that against me. It's a very residential hobbyist printer. But what I did is I compared the original scan file to the newly printed file, and I can see the exact deviations in different areas. And then by dragging my mouse over to location, I can see, hey, I don't have enough material here. I'm short by 200 microns. And if you're familiar with like the Enders, they're only good to about 200 microns. Yeah. So that lines up. But like areas which are green, we're right on. I can see here I'm off by 13 microns. I've got a little extra material over here. So I can see exactly where those deviations are, and I can even see, for example, the question had been on the holes, so I can see this hole is actually off by about 200 microns.
Cool. Yeah, and there's a question here. It's like kind of two related to the holes. do you print the part with the partial holes and then machine the part, or print the part without the holes? I would say, like, my preference is to, I want to rebuild it. There are certain things that you can do, I think, that, like in Mesh Mixer specifically, you can build a solid that is, say, it's just the hole with like a very slight perimeter on it. You could Boolean the two together, and then you've got yourself a bore through your part, right? So there are like fun mesh things that you can do. If you were to convert it into that solid body, you could then model a different surface and
put threads in there if you needed to.
Put the threads in there too, and like put it together. One of my favorite things to do, actually, when I'm trying to design threads into parts, like for a mesh, when you use the hole tool, it's not going to render the threads for you. But with the 3D printed part, some cases you can print the threads. I would say most of the time you don't. But in this case, let's say you're doing metal, you want like partial threads, you can do that. And I'll just take a part from, say, the McMaster catalog or Masumi or whoever, like whichever digital catalog you want to use. Take a positive part, say a bolt, like you have M3 bolts. Take an M3 bolt and then just do the Boolean, like fill it in and do a Boolean and remove the material, and then you've got yourself a thread. I would caution though, when you do that with these files and they get bigger and bigger, each time you do that, you're adding a ton of mesh points. So that's just something to be careful of.
Here's how I actually handle that one, coming from the opposite side of it, because I'm more familiar with using it in the mesh environment. I'll actually take the mesh, and then using like a sculpt tool, I'll actually make the hole a little bit smaller.
Yeah.
So I'll collapse the hole a little bit, and then I'll still print it. And what that gives me is it gives me a marker of exactly where the center of that hole is supposed to be, because it's still going to be the exact center point, and then I can drill out the material at that location with whatever the diameter should be for that hole.
Yeah. Does the software indicate features that it has certainly got right, and indicates features that it got probably right? Like the same vein that it indicates features that it certainly wants the human to revisit and correct. It's like, yeah, it's like, does the software like give you warnings about like imperfections or anything like that?
Yeah, so there's some ways in the software, for example, just to highlight, I don't have an exact example on here, but this is where there's something that it wasn't able to detect. And so it says, hey, I cannot measure this location.
Great.
I wasn't getting any data at this location. You can see it's not colored in or anything like that.
Yeah. So that's hopefully that answers the question. And we're about 5 minutes over. Thanks everyone for hanging on. If there are any other questions, I think there are still a few. Yeah, so there's a question about a starting point to get into industrial scanning, something low cost, like as a proof of concept, basically to convince the company to go full on for a more precise scanner. So like, I think, you have your offerings. And
and obviously the Keyence offerings are a little bit more on the high-end industrial end of the equation. There are some pretty neat scanners that are starting to come out. There's a couple that are like on the Kickstarter end of the world that you can get. There's also a couple of scanners that you can get for just like an iPhone. So anything that's a LiDAR-based camera has the ability to do scanning. Now, you're not going to get the greatest of scans with it. It's meant more for, hey, I'm going to scan a chair and get a representation of a chair. But if you're trying to showcase somebody, hey, this is what scanning can do, and just get your feet wet, you can pick some of those up just on like the App Store or the Google Play Store.
Yeah, my recommendation would be like, so I've done this before, and it's like I've also seen this happen before with 3D printing, and it's here's the issue, right? So you imagine that you're at a company and you tinker with 3D printing at home, and you've got an Ender 3, you got a Prusa. Like I've got one of each at home. But if I were to try to prove to Markforged or my previous employer that we needed to get a 3D printer, I wouldn't show them a part necessarily from a low-cost printer. Like if I want the precision and the strength of a high-end printer, like if I wanted Markforged strength, right? Like I don't want to show them a part that's like flexible like this, right?
Yeah, or like a PLA that just snaps in half.
Snap, right? At least this is durable, and it's like, but what I want to show them is this part, right? So Rob, show us what you think about each of these.
I mean, if I'm trying to make this as an obvious tool, that's just going to deform real quickly. So and then this guy, I'm going to hurt myself.
Yeah, that's not going anywhere. So my recommendation is not necessarily to go buy a low-end scanner and like try to justify why you need the expensive scanner. That's not going to get you the results you want. I would say go to a service provider and get a scan, right? You probably have a bunch of customers out there who offer scanning services. And what you want to prove is the concept. but the concept requires certain levels of accuracy, certain levels of repeatability, and certain qualities. Like, you don't want to start there. What you want to do is take your part, find a scanning service that will provide you reverse engineering services. They can either get you, there's like a bunch of ranges. I actually, I pinged our Facebook user group and asked people for recommendations. There, this is a good framework that I saw. There are 3 kind of tiers to reverse engineering services. There's mesh only, which is just going to give you just mesh. And that's something like, yeah, you could print as is, but it's not really reverse engineering. You could go to surfaces, which is giving you, that's taking that mesh body and converting back to mathematical surfaces to represent the part. The most complex, tier 3, is getting you parametric CAD. And really what you probably want, I would say like most people that are interested in this topic want parametric CAD. So you can pay for that service and it will cost less than the scanner that you buy. Like, you can go buy a cheap scanner, but like it's not going to get you the results you want. If you want like this level of quality, get the service done, take that part, show how that's working. And when you look at how much you're paying for services, that's a very easy way to justify the cost of ownership.
If you reach out to Keyence, we do have a list of service providers who can do scanning. So we'll be happy to send that information to you.
Something that I realized we didn't show during the live webinar was the scanning process. We figured that it wasn't something that was really that interesting to watch.
I don't know. I think we got too excited into getting into the actual process.
Yeah. So we want to kind of show you what that scanning process is like. Rob, would you mind sharing?
Yeah, absolutely. So, I mean, the whole concept to it is to make it fast, easy, and really, really accurate. So what I've got over here, this is the Keyence VL scanner. I'm just going to take my part, and I'm just going to place it onto the stage. Doesn't matter where it is. It doesn't matter if it has any markers or anything like that prepped up to it. And then I've got the software open here, and all I'm going to end up needing to do on the software side, I just want to make sure there we go, okay, is I'm just going to push measure right over here. And so you can see the part sitting here on the stage in the camera view. And then if you're looking at the live camera view of me, you'll actually be able to see it here. What the system's doing is pretty cool. So the first thing it does is a pre-scan of the part. And in that, it's actually looking for geometry that it recognizes. So it says, hey, I see a plane. I'm going to lower the resolution on the plane a little bit because I don't need to capture all the data there. You'll see it just did a turn. Well, it actually figured out for itself how to do that turn and how many degrees it needed to turn based on the geometry of the part. So it said, hey, there's an edge that I can't see. Let me rotate the part so that I can better see that. And you can see a generating file happening right here. So this is actually the live mesh being created and generated right there. So literally took the scan, cleaned it up, generated it, and then is going to go ahead and attach new data to that scan right now. The other thing that you might notice is once it's done with a scan, it hits it with a green light and a red light. And that's where it's getting the true color data of the part. So in all the scans that we showed, it's including not just the X, Y, and Z data for each of those data points, but also an R, G, and B data so that we grab things like, actually you can see here on the scan, there's some scratches and some tool wear marks and stuff like that on this part. So if those are important, great, they're being captured. If not, as we talked about in the webinar, sometimes we'll have to do some post-processing to say, hey, I don't really care about 10 micron flatness on a part. Yeah. So the total operation is designed to take about 3 minutes. It does change a little bit because the computer is actually building the scan plan for the operator. So they don't have to know, okay, let me set up this many rotations and I want to set this lighting exposure and this aperture setting and ISO settings and all the stuff you don't have to do on a traditional camera system. The other thing is that as it's scanning data, it's deciding how much resolution to hold of each of those geometries. So I talked a little bit about the fact that on like a plane, it'll decrease its resolution so that it's not capturing too much data. On a whole, it's going to increase the resolution because we know, hey, I need to capture, maybe there's a chamfer or a radius or something like that that blends into that hole. So we're going to increase the resolution at that location. One of the downfalls of scanners is that they generate massive amounts of data. And that's just kind of the classic problem with scanning technology today is that we've reached a point where we generate more data than a system can actually process, at least not in a reasonable amount of time. So a lot of scanners can take hours to go through the whole process. So part of the design here was to set it up so it would reduce the amount of data that it captures to the point where you're accurately grabbing the most important pieces, but you're not flooding it with just useless additional data. So the process it's doing right now is it's actually going in and it's cleaning up the files. So in this case, I didn't even count. I think it was 6. It automatically sets up how many rotations it does. I think it was 6 rotations. It grabs those rotations, it stitches the data together of each of those, and then it's looking for, where do I have duplicated data points? Do I have any holes that I need to try to mark as flagged and say, hey, I'm missing data here? Or do I have any locations where I need to smooth it out? I have some weird flyaways, things along those lines. And then once you're all said and done, there it is. There's your fully finished and generated file. Now, as I kind of showed in the webinar, it's a top surface, so I'm going to grab this, flip it over, push the button again, just for the purposes of helping everybody understand how this operates. I've already got that portion already grabbed, so I'm just going to grab the other half of this scan. We're going to have the first mesh that we just scanned right now. That's this guy right here. And then I have another mesh that I scanned ahead of time that's missing the back. And all I do is I click on something that occurs in both images. And there you go. Precise align that. And in about another 10 to 15 seconds, we're going to have a fully finished, ready to go file. And there she is. There's your full STL file, ready to get exported out and sent over to our software.
So you could probably use more than right. So we talked about on the webinar that there are certain features where you'd want to kind of angle it to get different shots. So if you wanted to and you needed more resolution or you needed like a very specific feature to be detailed, you could set it up to kind of look at that feature.
Right, and the process is the exact same. The stage even has the ability of tilting upwards. So like there's a hole that goes right through the center of this part that's a really critical kind of feature to this. So if I needed to, I could grab that, place it upright, and now it's looking straight down the barrel of that hole for the part.
Yeah, that's cool. Yeah, so I think that would probably alleviate some of the concerns that I was saying, where it's like you have a through hole that's like a really deep through hole. The scanner can't necessarily see it if it's aligned flat. And like if you were looking at it on a tabletop, you know, kind of staring at it and walking around, like you wouldn't be able to see it. But we, being resourceful humans and having a lot of degrees of freedom, can like look around and poke around. And again, inference. We're sort of inferring, we see empty space and reflection from the backside, probably smooth bore all the way through. So yeah, that's really cool. Yeah, thanks for the walkthrough.
Yeah, no problem.
If there's anything else that you want followed up on, please reach out to us. You can kind of reply to the webinars, the webinar reminder, I think, and somehow that'll end up back at us. If you need a reference, Rob's here, and so my email is charles@markforged.com. Rob?
You can reach me at rob.ortiz, it's ORTIZ, at Keyence.com.
Yeah, so we're here to answer questions, and thanks everyone for participating and joining today. Still got 180 people on the line.
Hey, we love a great audience. Thanks for all the great questions coming in, and we will get through all the questions and get responses back to people. Yeah, and this is the first part. I'd say we've kind of dug in, and I'm uncovering a lot more stuff that I want to cover. I think the thing that if there's one thing that everybody can take away from this is really brand new for so many people to understand, that we have come so far in just the last 3 or 4 years of technology that you and I can even have this conversation and start to do this sort of thing. And as people are learning more and getting more comfortable with it, only continues to improve. Better techniques will be found. But that's why I kind of started this whole presentation and this whole webinar by saying that we're so much closer to that Star Trek replicator kind of concept that people science fiction imagine than I think anybody thought we would be even 3-4 years ago.
Yeah, totally. And we'll do more of this. I think what will end up happening is we'll have maybe some videos on YouTube. So if you're not subscribed to us on YouTube, like go check that out. Markforged at YouTube. Keyence probably has a YouTube presence.
Yep, Keyence USA on YouTube. You can also find me on LinkedIn. I'm sure you can take a look at Charles on LinkedIn as well.
Yeah, and I'll be looking for suggestions. If you want to send those to us as to what we should cover next, like what's another topic that we should check out, like are there certain parts that you want that you're like, like that could be something that's reverse engineered. If you have any good ideas, like we're open to suggestions. I imagine we'll probably do maybe another video or two in like the coming months. So yeah, appreciate everybody joining us today. And Rob, thank you for being here and for helping us talk about this. Yeah,
I love talking about new technology in the future and where we're going. So it's my pleasure.
All right, sweet. Thanks everyone. Have a good day.